In this problem, we're going to solve the one-dimensional Quanton in a box problem, also known as the infinite square well. Now, let's contextualize what I mean by solve. And to do that, let's go back to the very beginning where we had the original Schrodinger equation. This is a partial differential equation that has partial derivatives with respect to position and partial derivatives with respect to time. To attack this general problem, we applied the separation of variables technique, where we assumed that this capital psi, which could in general depend on position and time, could be factored into a part that depended only on position and a factor that depended only on time. Doing that got us two equations, one that depended only on position, that's this equation, also known as the time-independent Schrodinger equation, and one that depended only on time, which we solved and got this expression. Okay, so we don't have to go all the way back to the beginning. Every one-dimensional quantum mechanical problem starts here, but to every one of those problems we can go through this solution method and already have the time part. So we don't have to do this again. This is sitting here waiting for us. What we need to do in this problem is apply or put into the time-independent Schrodinger equation the specific form of the potential energy function for the problem of interest. So what that means is, for the Quanton in a box, we have to define what we mean by that in terms of what is the potential energy function, and hopefully write it in terms of x. And then we can go about solving this time-independent Schrodinger equation to find the energy eigenstates, these little psi's. So let's go about doing that now. So here's the Quanton in a one-dimensional box potential energy function. This is the world's simplest quantum mechanical bound state problem that anyone has ever thought of. So here it is. We plot the potential energy on this axis as a function of position on this axis. And in the region between x equals 0 and x equals L, the potential energy function, the potential energy as a function of x is 0. But at x equals 0 and at x equals L, the potential energy goes to infinity. And it's infinity for x less than 0, it's infinity for x greater than L. So that's our potential energy function. So now let's look at that in the context of our time-independent Schrodinger equation. First, let's consider the case x less than 0 and x greater than L. So we're considering this region and this region. In that region, the potential energy function is infinite. So in order to get it balancing infinity here and end up with something finite here, this wave function basically is going to have to be 0. In other words, we have to match this infinity with a negative infinity right here. Now that's not very rigorous. That's just an arm waving argument. A more rigorous argument will show that in fact the wave function is in fact 0 here and here. In this context, when I say wave function, actually, of course, remember we're talking about the spatial part of the wave function. So the spatial part of the wave function is 0 in this region. Now in the case between x equals 0 and x equals L, in that region, the potential energy function is 0 by definition in the problem right here. And so our time-independent Schrodinger equation becomes this, where we have 0 in place of the potential energy function. We can rearrange this. So here we see that the second derivative of little psi with respect to x is equal to the negative of some constant times little psi. Since all this in here is positive, it's convenient to write that in a way that makes it look positive. So we'll define a new constant k such that k squared is 2me over h bar squared. With that, our time-independent Schrodinger equation becomes the second derivative of little psi with respect to x is equal to minus k squared times psi. So we need to find some function, little psi, that when we take two derivatives of it with respect to x, we get back that function and a minus sign and a factor of k squared. Some specific solutions to this differential equation are sine of kx, cosine of kx, e to the I kx, and e to the minus I kx. any of these functions, if we take two derivatives of them with respect to x, will give back the original function, a factor of k squared, and a minus sign. Now this is a second order differential equation. We can put together any two linearly independent specific solutions, some linear combination of them, in order to get a general solution. And there's lots of ways we can do that. It turns out the most convenient way to do that will be to use the sine and the cosine, like this. I should also point out that e to the ikx and e to the minus ikx are also linearly independent, so we could have written the general solution this way. So it must be true then that if I could write the general solution in either of these two ways, that we ought to be able to go from one to the other if we wanted to. I'm not going to show that. That can be shown if you want to work it out yourself. We're going to use this form of the general solution here. It'll turn out to be more convenient than this one here. So that's what we're going to do. So now that we have a general solution, we need to apply our boundary conditions. We'll apply this boundary condition first. The spatial part of the wave function at x equals 0 is equal to 0. Applying the first boundary condition, we get that 0 equals a times 0 plus b times 1. That means the only way to solve that is that b is equal to 0. Using the fact that b is equal to 0, we're left with a sine kx for our wave function, but now we can apply our second boundary condition that the wave function vanishes at x equals L. So we do that here. The little psi of L, the spatial part of the wave function at L, is equal to 0. So that means a sine k times L, plugging in L for x, must give us 0. Now, the sine function vanishes when the argument is a multiple of pi, so pi or 2 pi or 3 pi, etc. So we can call that n pi. Solving for k, we get k is equal to n pi over L. Actually, the n equals 0 value also works. If n is equal to 0, you would just get k is equal to 0. Of course, if k is equal to 0, you just have sine of 0 for every value of x. That just boils down to saying that the wave function, or the spatial part of the wave function, is 0 regardless of the value of x. That of course works. That's just a solution where you basically have no probability of the quanton being found anywhere. That is, no quanton at all. This is known as the trivial solution, so we normally don't include it in our solution here. Plugging in for k in the expression for our state function right here, and again remembering that b is equal to 0, we get that the energy eigenstates have the functional form psi sub n of x equals a sine n pi x over L, where n can take on the values 1, 2, 3, 4, etc. Plugging these allowed values of k into this expression that relates k and the energy, we can solve for the allowed energies. If we do that, we find that E sub n, which is the eigenenergy corresponding to the eigenstate psi sub n, has an energy of this form, again where n could equal 1, 2, 3, 4, etc. Note that this means that there are only certain allowed energies. We can't just have any old energy. We could have energy E1, plugging in 1 squared here, or E sub 2, plugging in 2 squared here, or E sub 3, plugging in 3 squared here, etc. We can't just have any old value of n. We have to have these values 1, 2, 3, 4, etc. This phenomenon is known as quantization of energy. It is not a unique or special feature of the quanton in a one-dimensional box problem, but rather a general feature of bound quantum mechanical problems. Finally, one last note. If we wanted to, we could find this constant a by ensuring that this state function is normalized. That is, we know that there should be a probability of 1 of finding the quanton if we were to make a measurement of the position between x equals 0 and x equals L. So in applying that condition, we could figure out what a is. All right, thanks for watching.